Welcome back, everyone, to our continued discussion of the theory and intuition behind support vector machines. In this lecture, we're really just focusing on the intuition behind the use of kernels. Kernels allow us to move beyond a support vector classifier and use support vector machines. All the examples we've seen previously have either been a maximum margin classifier or a support vector classifier that allows the use of soft margins. We haven't actually seen a support vector machine yet. That is because it is the kernel operation that allows us to move beyond support vector classifiers to support vector machines. And there are actually a variety of kernels we can use to project the original features to a higher dimension. Let's explore and get an intuition of how this all works through some visual examples. Recall our one-dimensional feature example of classes not easily separated by a single hyperplane. Here we have some feature x, and then the two classes we have are noDefault on alone and defaulted on alone. And keep in mind that along this single feature, there's not a single point or hyperplane along a one-dimensional feature that would easily separate out these two classes without having to have a bunch of misclassifications. So what we can do is explore how to use a kernel that could project this feature onto another dimension. For example, we could use a polynomial kernel, which could expand this onto an x squared dimension. So if we imagine that maybe the noDefault feature value is kind of centered around 0, and people with large negative feature values or very large negative feature values are going to default on their loan, if we were to take these original points and project them using this polynomial kernel of x squared, we would get something that looks like this. Now, we could create a hyperplane, again using margins, and even incorporating soft margins onto this projection, and after we perform this transformation. And notice how we were able to take something that was not perfectly separable, and then actually create something that was perfectly separable in this particular case using this kernel projection. Which means we now have the ranges that we're going to classify someone as a noDefault or default. So using the kernel projection to evaluate a new point would look something like this. We would see where that new point lies on this original one-dimensional feature, and then project it to the x squared using something like the polynomial kernel. And in this case, we would classify this as a default. And now we can see how we can deal with class points that are not easily separable through the use of a kernel. We can also explore how this example works in 2 dimensions. We can imagine a 2-dimensional feature space with features x1 and x2, where again, there is no hyperplane that can actually separate this effectively, even if we incorporate soft margins. Notice one of the class points is kind of centered and the other class points are surrounding it. So what we can do? Well, with the use of support vector machines that allow us to enable a kernel transformation to project again to a higher dimension. And we can imagine this that we're going from something like 2D to 3D, where we're projecting onto a higher dimension, almost curving these points along their surface, and then finding a hyperplane that would be able to separate this out. We can think of this as maybe having a bunch of balls on a cloth and then tossing the cloth in order to throw the balls into the air and then finding the hyperplane that would separate these while they were in mid-air. Now you may have also heard of something called the kernel trick, which is something around the mathematics of the use of kernels in support vector machines. We previously visualized transforming data points from one dimension into a higher dimension, such as taking the original feature x and then projecting it with x squared. Now, this itself is not actually the kernel trick. Mathematically, the kernel trick actually avoids recomputing the points into a higher dimensional space. What we just showed you was essentially a visualization of the use of kernels. But if you've heard the term kernel trick, it's actually talking about using dot products to avoid the expensive computations associated with having to transform everything with a kernel. So how does the kernel trick actually achieve this? It takes advantage of what we just mentioned, which were dot products of the transpositions of the data. And recall, all the way back in our historical discussion, there was a 1964 paper that also noted the same thing. And in the next lecture, we're going to go through some of the basic mathematical ideas behind this kernel trick. I'll see you there.